I'll be presenting task 1 of our signal and system project, which is about the convolution of a one-dimensional audio signal. So this task gave me hands-on experience with audio signal processing using MATLAB as the software. Tools and steps. For this task, I used MATLAB, more specifically R2025A version, and I recorded my friends and my voice and my friend's voice using a mobile phone microphone. Since I recorded the audio was in stereo, I converted it to mono to make it a one-dimensional signal, which is required for convolution. Next, I define a simple impulse response. For example, 1, 0.5, and lastly 0.25 to represent how a system fades or echoes a signal. Then I use a MATLAB built-in conv function to convolve the voice with the impulse response. Lastly, I normalize the output signal to avoid distortion and played back the original, the impulse, and lastly the convolved signal for comparison. So, step 1, which is reading and pre-processing the audio. First, I read the recorded audio file using audio read. Since some of the recording may be stereo, I check if the signal has two channel using size, voice, comma, 2 equals 2. If it does, I converted it to mono by averaging the left and right channel using mean. This ensures that we're working with a 1D signal, which is required for the convolution operation. So step 2, I define the impulse response as 1, 0.5, and lastly 0.25. This simulates a basic systems with decaying feedback, like an echo effect. So step 3, which is convolution using conv function, which mathematically combines the input signal with the impulse response. After convolution, I normalize the output by dividing it with the maximum absolute value to prevent audio clipping. So step 4, I played back all three audio signal, which is the original voice, the impulse response, and the convolve output using the sound function. So step 5, here I plotted all three signals using MATLAB subplot function. So let me explain the result visually after I run this MATLAB code.
B1222320049. B1222320011.
B1222320033.
B1222320014.
B1222320049. B1222320011.
B1222320033.
B1222320014.
Okay. So let me explain the results visually. At the top, we have the original voice signal. You can clearly see the waveform structure that represents the spoken words. In the middle, we have the impulse response. It's shown using a stem plot because it's a short, the discrete time signal. So at the bottom, we see the convolved output signal. It closely resembles the original voice but has a trailing effect. This is due to the convolution, which spreads the original signal based on the impulse response. So that is all from me. Thank you for listening.
For this task, we were asked to apply Fourier series to compose a simple 10-second song using harmonics of sinusoidal signals. But instead of explaining it first, let me play you a short melody we composed using MATLAB. Assalamualaikum and good afternoon to Dr. Julita. And yes, that was the Baby Shark melody, but not recorded. It was synthesized using code and sinusoidal harmonics. This is the waveform of the full Baby Shark melody. As you can see clearly, the more complex shape resulting from combining multiple harmonics are a direct result of Fourier series synthesis. Here we generated the first four harmonics of musical notes. The first harmonic is the fundamental tone. The second and third harmonics are multiple of that base of the frequency. And fourth harmonic gives us a lower tone layer. These harmonics are combined to create a richer, more musical sound. This block diagram summarizes our process. Set the sampling rate and duration. Second, create the time vector. Generated H harmonics, harmonic 1, harmonic 2, harmonic 3, and harmonic 4. Play them individually for demonstration, and then combine them to form the final melody. Finally, we plotted the waveform for analysis. In conclusion, this task has shown us how basic math like sine waves and harmonics can be used creatively to synthesize music. We not only learn signal processing but also gain hands-on experience in composing through code using MATLAB. That is from me. Thank you.
Hello, my name is Muhammad ISKANDAR. This is task 3 fast Fourier transform. This is the coding for task 3. Line 2 and 3, the image is read from the specified path, displaying the original image. Line 4 and 5, the image is converted to grayscale. Line 8, this computes the 2D Fourier transform of the grayscale image. Line 10, this magnitude spectrum indicates how much of each frequency is present in the image. Line 12, magnitude spectrum correspond to dominant frequencies which relate to edges, texture and patterns in the spatial domain. Line 14, this function shifts the zero frequency component, DC component, to the center of the spectrum. Line 18, the log transformation is applied to the magnitude spectrum. Line 22 and 23, moving the zero frequency component back to its original position in the frequency domain, and the inverse Fourier transform is computed to reconstruct the image from its frequency representation. Image is read from a file and displayed in the context of Fourier transform. This image represents a signal in the spatial domain where pixel values correspond to intensity levels. Converting the image to grayscale simplifies the data by reducing it to the signal channel. This is important because the Fourier transform operate on intensity values, and a grayscale image provides a clearer representation of the signal intensity variation. The Fourier transform decomposes the spatial signal image into its frequency component, allowing us to analyze the image in terms of its frequency content. The centered spectrum allows us to see the low frequency components, which represent the overall structure of the image in the middle, and the high frequency components, which represent fine details at the edges. The log transformation is applied to the magnitude spectrum to enhance visibility. Next, Fourier transform of context. This step is particularly useful in image processing, and it allows us to see subtle details in the frequency spectrum that might otherwise be overshadowed by stronger frequency. Finally, the inverse Fourier transform is used to rebuild the image from its frequency form. This shows that the process can be reversed and the important details of the original image are kept. For conclusion, first, grayscale conversion simplifies the image for easier frequency analysis. Second, 2D Fourier transform reveals important frequency components showing edges and textures. Third, spectrum centering and log scaling enhance visibility of subtle details in the frequency domain. Fourth, inverse FFT confirms accurate reconstruction, highlighting Fourier transform usefulness in image processing tasks like filtering and compression.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irsyad bin FITHRI Aziz, and I'm going to be continuing my part for task 4, which is the convolution of 2D dimensional signal. Okay, so for task 4, it can be divided into two parts. For the first part being the grayscale conversion or the blurring, and then the second part is the LOG or the Gaussian. First of all, we've taken the picture from all 4 of our members, and then from there we have obtained this coding. So for blurring with the Gaussian kernel, so first the grayscale conversion, so it basically checks, this code checks if the image has 3 color channels, whether an R, G or B. So if so, it converts the image to grayscale using RGB to gray command. Okay, and for line 9, it defines 4 different standard deviations for the Gaussian and LOG kernels. So the standard deviation, it controls the spread of the kernel, and it affects the degree of blurring and edge detection. So this is the result from what we have obtained using the coding that we used earlier. So this is the original image, as you can see. So for the first standard deviation, it provides a slight blur where the image retains more of the details. For the second one, it's a moderate blur, and fifth one is a significant blur with fewer details visible. And then for the 10th standard deviation, it has a very strong blur where most of the image's details are lost. Now we move on to the next part, which is the Gaussian and LOG kernels. So using the same coding from earlier, we just added some adjustments and additions to the coding so that we can use the same picture and now just alter it so that it provides edge detection that we desire in this part. So the LOG kernel calculation, the Laplacian of Gaussian kernel, is computed using this formula right here. Okay, so log xy equals to frac 1 pi sigma to the power of 4 times 1 minus x power of 2 plus y power of 2, and then divided by 2 times sigma the power of 2, and then exponent plus y power of 2 divided by 2 sigma power of 2. So from this, we have obtained these results. So this is the original image. So from there, for the first standard deviation, the edges are very sharp and very precise. So for the second one, it has a slight smoothing of edges where some finer details are lost. For the fifth standard deviation, the edges becomes more blurry and some features are no longer distinguishable. But for the 10th standard deviation, only the most prominent of edges are detected. So with the rest of the image fading into the background. Okay, so what we can conclude from this task is that for the first part, Gaussian blur, the larger the standard deviation, so the more the blur, which means less detail. The smaller the standard deviation, it means less blur or more detail. For Laplacian of Gaussian or GLOG, edge detection combines blur and edge detection. So the smaller the standard deviation, the sharper it is. So more detailed edges. The larger standard deviation, the smoother it is, and it highlights only the strong edges. Okay, so that's basically it for my part, and thank you very much.